Hello friends, welcome to this lecture on computer aided power system analysis. So far we have looked into the process of Y-bus, process of building up of Y-bus matrix of a 3-phase unbalanced system, including transmission lines as well as the transformers, and after that we have looked into the process of finding out the fault admittance matrix of different types of faults, and then subsequently we have looked into that how to perform the fault analysis in the phase domain. Now, in this all this analysis we have essentially assumed that this transformer admittance matrix, which is nothing but a 6 by 6 matrix, is actually already known to us. For example, we said that any transformer can be modeled as any transformer. For example, if I have an transformer A, this is basically a 3-phase transformer. So, this is basically a 3-phase transformer. So, here we have Vp ABC, and here Ip ABC, and here we have let us say Vs ABC, and we have let us say Is ABC, and then we have said that Ip ABC, Is ABC, we have said that this can be represented as some 4 matrices that we have said. We have said that we assume that with this admittance matrices are known, and based on that we have looked into the process of including this transformer admittance matrix into the overall Y-bus matrix of the entire system. Now, we have assumed that this matrix is to be known. Of course, this is 6 cross 1 because all of them are 3 cross 3. So, this is 6 cross 1 and this is also 6 cross 1, and individually all these matrices are 3 cross 3, all these matrices are 3 cross 3, all these matrices are 3 cross 3, they also 3 cross 3. So, that we know. Now, today we will be looking into that looking into the process of finding out these 4 matrices given any transformer connection. For example, suppose we say that we have a transformer connected as YG 0. This means that this primary side this is primary side grounded, primary side, this is YG, this is the secondary side YG, secondary side also YG. So, what we are doing is that we are denoting the primary side as the capital, we are actually denoting the primary side with a capital letter, and we are essentially denoting the secondary side with a small letter. This G stands for that this is connected in star grounded fashion, and this is also essentially denoting that the secondary side is also connected in star grounded fashion. The 0 denotes the phase difference between the corresponding phases of primary and secondary side. So, as we know from our basic analysis of transformer vector group, that this 0 means that essentially the phase difference between the primary side and the secondary side between the corresponding phase voltages is 0 into 30 degree. So, that is essentially 0 degree. So, then therefore, if I have another connection, let us say YG say 4. So, then therefore, what we will simply know from this connection or rather from this notation is that here also our primary side is connected in star grounded fashion. Here also our secondary side is connected in star grounded fashion, but there is a phase difference between the phase A voltage of the primary side and the phase A voltage of the secondary side, and this phase difference is 4 into 30 degree, that is equal to 120 degree, right. So, then therefore, now so then therefore, we need to look that what would be the transformer admittance matrix, that is this matrix, if we denote, let us say this is the, if we denote that this is Y tran. So, then we need to find out that what would be this transformer admittance matrix, that is Y tran matrix for this connection, or let us say this connection, or for let us say any other connection. So, that is the objective of this lecture as well as the next couple of lectures. So, let us start with the simplest possible connection, that is YG 0, and then we will try to see for other types of connections if our time permits. So, what we are now doing is that we are now trying to consider that how to develop the transformer admittance matrix for a given transformer connection. So, to start with, we are taking that YG small yg 0. So, this is the transformer. So, now because this is a 3-phase transformer, we assume that any 3-phase transformer is actually consisting of 3 single phase transformers. So, then therefore, we do have 3 set of primary winding and 3 set of secondary winding. So, let us say that we do have this 3 set of primary winding as these are the, so these are the right. So, let us say we do denote these terminals as A1, A2. This terminal is denoted as capital B1, capital B2, and this terminal is denoted as C1, C2. And similarly, these terminals are denoted as small a1, small a2. These terminals are in small b1, small b2. This is denoted as small c1, small c2. Now we know that for any transformer to be represented correctly, we also need to put a dot on the windings of the transformer. So, then let us put that there are dots at this point and at this point, dot at this point, dot at this point, and dot at this point, dot at this point. So, what is the significance of this dot convention? Significance of this dot convention is, if we do recollect, so let us say this voltage Vp here, so this voltage Vp, and if this voltage is Vs and Vp and Vs. So, then this Vp and Vs are in phase. So, when I say that this voltage Vp means potential of this point as compared to this point, as well as potential of this point as compared to this point, these are in phase. So, then therefore, this voltage in this direction and this voltage in this direction, they are in phase. Similarly, if the current here entering is, let us say Ip, and if the current going out of this is IS. So, then this IP and IS are also in phase. So, this is the convention of the, so this is the dot convention. So, we say that this is nothing but the, this is the dot, this is the dot convention. So, this is the dot convention, right. Now, one thing we again have to recollect, if I say that this voltage and this voltage they are in phase. So, then therefore, when you would be drawing the phasor diagram of this voltage and this voltage, they should be drawn as parallel lines to each other. So, similarly, this voltage and this voltage, because these two are in phase, that is basically this voltage with respect to this point and this voltage with respect to this point, because they are in phase. So, then therefore, these two voltages also should be drawn in parallel to each other. Similarly, these two voltages also should be drawn in parallel to each other, because they are in phase. Now, our connection is YG 0. So, then therefore, we first make the connection at the secondary at the primary side. So, we make the connection in the primary side as, so make the connection in the primary side. So, what we do is that we simply join these and make it to grounded. So, what we are doing? So, now what I have now, so after I join this, after that we draw the phasor diagrams, after that we draw the phasor diagram. So, now let us draw the phasor diagram. Phasor diagram. So, what would be the phasor diagram at the primary side? This is a this and this. So, this is grounded. So, let us say this terminal. So let us say that this point is A1, this point is A2, this point is B1, this point is B2, this point is capital C1, this point is C2. So, then from this diagram what we can see that essentially, so now what we have done is that we have as if put these three winding in the appropriate fashion, and what we are doing that we are simply connecting these terminals A2, B2 and C2 together, and then simply shorting this connection to ground, and that is what exactly we have done. We have simply shorted A2, B2 and C2 together, and then that short connection we have connected to ground. So, then therefore, and this is my phase A. So, essentially this is my phase A, this is my phase B. So, this is my phase C. So, we can see that this is my phase A and this is my phase B at the primary side, and this is my phase C. So, then therefore, at the primary side A1 terminal denotes phase A, B1 terminal denotes phase B, C1 terminal denotes phase C. Now, the point is how do I make the connection at this site. So, for that what we have to do, that we have to now draw the vector diagram at the secondary side. Now, we are saying that this side is also star grounded, and the phase difference between the phase A voltage of the primary side and the phase A voltage of the secondary side is 0. So, then therefore, the phasor diagram at the secondary side also would be exactly similar to this. So, this is basically phase A voltage. If this is the phase A voltage, so then therefore, this voltage should be in parallel with this voltage. Similarly, this voltage should be in parallel with this voltage, and this voltage should be in parallel with this voltage, and that is what precisely we have done. Now, because these two are parallel in nature, so then therefore, and we have also said that from this dot convention, when terminal A1 is positive with respect to terminal A2, at that instant terminal small a1 will also has to be positive with respect to terminal small a2, right. So, then therefore, if this is capital A1 capital A2 and because these two are in parallel. So, then therefore, this also should be A1 A2. So, this terminal also should be A1 A2. Similarly, if this is B1 B2, I mean this point is B1 and this point is B2, and because these two and these two would be parallel. So, then therefore, their orientation of this winding and this winding also would be in parallel. So, then therefore, this is B1. So, this terminal is B1 and this terminal is B2, and similarly this would be small c1 and this would be small c2, and because it is grounded. So, we make them grounded, correct. So, then what we are doing? So, from this vector diagram what we are doing is that essentially we are connecting A2, B2 and C2 together. So, we are connecting A2, B2 and C2 together and shorting that connected terminals to ground. And if this is phase A, so then therefore, this is also phase A. So, then therefore, at the secondary side also this is phase A, and if this is phase B at the primary side. So, then therefore, this is also phase B. So, then therefore, from B1 we also take phase B, and from C1 similarly we take phase C, correct. So, this is the vector diagram and this is the corresponding connection, right. Now, if I say that this voltage is VA and this point is grounded, now let us see what happens. Now, from this particular circuit diagram what you can see, if I say that this voltage is VA, if I say that this voltage is VA, if I say that this voltage is VA, so then therefore, this point would be VA because this point is already grounded. Similarly, this point voltage would be VB, similarly this point voltage would be V capital C. Similarly, this point voltage would be V small a, this point voltage would be V small b, and this point voltage would be V small c, right. And now, let us denote that this is I A, that is the current which is entering the phase A voltage at the primary side. So, this current is I A. Similarly, this current we denote as I capital B. So, that is the B phase current at the primary side. Similarly, we denote the current I capital C, and in the same token, same vein, the current which is going away, or rather which is going towards the phase A terminal in this direction away from the winding, we will say that is I small a, because as we have said we denote the secondary side with small letter and we denote the primary side with capital letter. So, this current is I small a, this current is let us say I small b, and this current is I small c. So, then therefore, from this arrangement and this circuit notation and this phasor diagram and this circuit, we can easily say that I A and I A they are in phase. Similarly, I B and I B they are in phase, and I capital C and I capital and small c are also in phase, right. Now, here this transformer ratio, let us say nominal ratio is 1:1. Please understand that because we are doing everything in per unit. So, then therefore, this nominal ratio in per unit will be 1:1. In any case, we are also taking it at 1:1. So, in per unit it is 1:1, That means basically if I give here a per unit voltage 1 per unit, I would also get 1 per unit voltage here, right. So, in per unit this is 1:1. Of course, in actual value this could be vastly different. For example, this for example this can be, let us say, a 400 kV, and let us say this can be, let us say, a 33 kV, right. So, in actual value these two winding voltage rating could be vastly different, but in per unit they would be 1:1. Now, because these are in per unit, so then therefore, I can say that this current I A and I A would be same. Similarly, current I B and I B would be same. Similarly, current I C and I C would be same, because they are in per unit. They would be the same. In per unit they would be same. In per unit they would be same. So, that means if I give in 1 per unit current here, I will also get 1 per unit current here. Now, suppose the transformer leakage impedance is Y. This is the transformer impedance, transformer admittance. This is the transformer admittance. It is basically transformer leakage admittance. So, what is that? So, essentially what we are doing, we know that for a transformer there is essentially series branch and also there is a basically magnetizing shunt branch, right. But here in this analysis we are simply neglecting the magnetizing shunt branch. So, then therefore, what we are getting? So, from point A, so this is point A and so this is point A. So, then we would be getting some impedance, right, some impedance Z, and Y is nothing but Y 1 by Z. Here essentially magnetizing shunt branches are neglected. So, here transformer, so we should write that transformer magnetizing shunt branch is neglected. So, now what we have done, that in this particular diagram we have essentially represented this particular diagram, this particular transformer by its equivalent circuit like this and this. So, this point is V A, this point is V small a, and this, and between A and A there is a transformer leakage admittance, that is Y. So, then therefore, if I have a current I A here, right. So, then I can have I A is equal to Y into this voltage difference, Y into V A minus V A. Similarly, if I B also would be Y into here. So, now what happens? So, now the current I B which would be entering here would be nothing but this voltage minus this voltage into this transformer shunt admittance. So, it would be Y into V B, V capital B minus V small b, and I C would be is equal to Y into V C capital C. Please note V small c, we should write it as capital C. We should, unfortunately for capital C and small c, there is not much of a difference in shape, there is only difference in size. So, therefore, you should be little more careful. So, I A is equal to Y into V A minus V A, and I B is equal to Y into V B minus V B, B capital B. So, this is the primary side, this is the secondary side, and we are calculating everything in per unit. So, then what would be I A? Now, what would be I A? I A would be nothing but is equal to I capital A, because this is an 1:1 transformer, we have already argued here, because this is an 1:1 transformer. So, then therefore, I A would be equal to capital A, and they also would be in phase to each other. So, then therefore, I A would be is equal to capital A and so then therefore it is y into VA minus VA. IB is equal to I capital B is equal to y into VB minus VB, and I C, this is small c, is equal to I capital C, that would be y into V capital C minus V small c. So, what we have that we have got, so now we have represented all these 6 currents, I capital primary current and secondary current, in terms of this primary side voltage and secondary side voltage. So, then here in this case my I primary ABC would be is nothing but IA, I capital B, I capital C transpose, and IS ABC is I small a, I small b, I small c transpose. Similarly, V primary ABC is V capital A, V capital B, V capital C transpose, and V small s secondary is V small a, small b, small c transpose. Now, here one thing we need to remind ourselves, we have done a mistake. Here we have actually done a mistake. What we said actually this current direction is not in this direction, this current direction is not in this direction, this current direction is actually in this direction, because if we do remember what we said, that I do have an bus I and J, and then we do have a transformer, right, and we said that this current is IPABC and this current is IS. So, then therefore at both the sides current is entering into the transformer. So, for this transformer model at both the sides current was entering into the transformer. So, then therefore, this is IPABC and this was ISABC. So, both these sides current is entering into the transformer. So, then here to note this ISABC would be current entering in the transformer. So, it would be minus IA, minus IB and minus IC, because here in this diagram IA, IB, IC are going out, but for this transformer model it should be go into the transformer. So, then therefore, ISABC would be minus IA, minus IB and IC transformer, right. So, now with this notation, if you now write down these equations in a matrix form, what do we get? We get IA, IB, I capital C, then minus IA, minus IB, minus IC, and then something we will write. What is that something? So, this is VA, this is VB, this is V capital C, this is V small a, this is V small c, this is small c. Now, IA is equal to 1, and so that should be now everything is actually multiplied into y by y. So, then we can take this y as a common. So, we take y as a common. So, we take y as a common, so 1, then 0, 0, and then it would be minus 1, 0, 0 for IB 0 1 0 0 minus 1 0, for IC 0 0 1 0 0 minus 1. What is minus IA? Minus IA is nothing but minus IA plus A. So, this is nothing but minus 1 0 0 then 1 0 0. Similarly, it would be 0 minus 1 0 then 0 1 0 and it would be 0 0 minus 1, right. So, it is 0 0 minus 1 and then 0 0 1. So, this is the admittance matrix. So, this is the representation. So, now here we have to locate everything. So, then therefore, this is nothing but IPABC and this is nothing but ISABC. This is nothing but VPABC, this is nothing but VSABC. So, then therefore, now if I do partition it, so then therefore, this is, so this portion is Y1, so this is Y1. So, if I do partition it, so then this is Y1 matrix, this 3 cross 3 matrix is Y2, this 3 cross 3 matrix is Y3 and this 3 cross 3 matrix is Y4. So, then therefore, what we can see that Y1 is equal to actually an I3, Y2 is actually minus I3, Y3 is also minus I3 and Y4 is actually I3. Now, what is I3? I3 is the 3 cross 3 identity matrix. Right. So, then therefore, for an YG 0 transformer, just from the very basic principle of transformer modeling and the phasor diagram and the very basic operational principle of the transformer, right, we can directly derive all these 4 submatrices, right. So, it is so here actually we really do not have to remember anything, just following the basic principles of this transformer operation we can simply derive this transformer matrices. So, we stop here today, and in the in the next lecture we will be also looking at some other example of transformer modeling. Thank you.